All right, welcome back. Now, at the end of the last video, I had you go ahead and solve the next three before you started this one. So I went ahead and worked them out ahead of time, and I will reveal the answers now. To solve the equation, justify each step. 6x minus 11 equals negative 35. So we write the first equation, we write the equation because it's given. We start at the beginning with what we're given. Then we want to add 11 to each side to get the x by itself. That's our addition property. We're going to simplify and combine like terms. So we get 6x minus 24. And then we're going to divide by 6. That's our division property. We end up with x equals 11. Check your work, but I'm sure it's looking great. Question 2 that you already took care of. Solve the equation, justify each step. 39 minus 5z equals minus 1 plus 5z. All right, first things first, we write the equation because it's given to us. Then we want the z's on the same side, so we're going to add 5z to both sides. That's our addition property. We're going to simplify, combining like terms, ending up with 39 equals negative 1 plus 10z. Then we're going to add 1 to each side to get the z by themselves. So that's our addition property. Once we simplify, we end up with 40 equals 10z. We divide by 10, z equals 4. That's our division property. Last one that you were doing on your own. All right, first thing, solve the equation, or write the equation exactly like it's given to us, because it is given to us. Then we're going to distribute. And here, I distributed both sides, both the negative 3 and the 2. I distributed them both. If you want to do one at a time, that's still legal. If it's more comfortable doing that, then do it that way. Our distributive property. Then we want them on the same side, so we're going to add 8r to both sides, our addition property. We're simplifying again, combining our like terms, ending up with 2r plus 15 equals 18. Then we're going to subtract 15 from both sides, and we end up with 2r equals 3. I understand you're not going to simplify, write it all out and simplify every time. So I bent to reality on this one. And then after we do that, we're going to divide by 2. And we're going to end up with a final answer of r equals 3 divided by 2. That's our division property. So hopefully as you check your work, you're just working through the process and not worrying about what the numbers or letters or other things are. We're only worried about doing the process. So let's apply this again. So here we have the formula for the area of a triangle. And we want to solve it for b. So just like with the r, we want to solve for b. So we need to end up with b equals something. We're going to justify each step. Same, we're going to give the property we're using. And then we're going to find the base of a triangle. We have the area and the height. We will plug those in at the end after we get b equals, because then it won't complicate things. It won't muddy the water at all. So let's start with what we're given. A equals 1/2 base times height. That's our given. Well, I don't know about you, but everybody I know hates fractions. So let's multiply through by 2, both sides by 2, and get rid of that fraction. So we got 2a equals base times height. That's our multiplication property. All right. So to get the b by itself, because we need b equals, we have b times h. So we got to get rid of the h, we got to, instead of multiplying it by it, we got to divide by it. So we get 2a divided by h equals b. That's our division property. And we want it b equals, not equals b, so we need to flip it around. And as we learned in a previous lesson, we can do that via the symmetric property. So we're going to bring that guy out of mothballs and use him as a hint at what the things to come. So now that we got b equals, now let's substitute in our numbers. So we get b equals 2 times 952 divided by 56. That's our substitution property. And then we just have to do the math. 2 times 952, it's going to be 1904 divided by 56. B equals 34 feet. We do the same equation process we've always done. Now we're just giving reasons for stuff. But we have other properties of equality we can use. And we'll talk about them in a second, but we just want to reiterate, properties of equality are true for all real numbers. And segment lengths and angle measures are real numbers. So we can use the property of equality for segment lengths and angle measures. And just as a reminder, we have AB, that is equal to the length of segment AB. So it's going to be a number. If we have the measure of angle A, that is the measure of angle A, it is also going to be a number. So we get to treat it like a number. So here, when we're using our properties of equality, we get to apply them to segments as if they're numbers. Because if we're talking about lengths and measures, they are indeed numbers. So let's remember what our reflexive property is. If we have real number A, it's going to equal real number A. So how does that apply to segment lengths? Well, segment length AB, it's going to equal AB. The measure of angle A is going to equal the measure of angle A. Simple enough. The symmetric property is the same in both directions, both coming and going. So if real number A equals real number B, then real number B equals real number A. That's how we can flip around an equation the other way, like we did up here, right? Like we did up here, to get it pointing in the right direction. So if we're dealing with segment lengths, if AB equals CD, then CD equals AB. And with angle measures, if the measure of angle A equals the measure of angle B, then the measure of angle B equals the measure of angle A. Same rules apply. So the transitive property, which of course is our favorite, so if A equals B and B equals C, then real number A equals real number C. So in segment lengths, same thing. If AB equals CD and CD equals EF, then AB is going to equal, then AB is going to equal EF. And if we're dealing with angles, nothing changes. The measure of angle A equals the measure of angle B, and the measure of angle B equals the measure of angle C. Then the measure of angle A equals the measure of angle C. So keep it simple, things don't change. So let's see if we can use these to our advantage. Let's make it more complicated. So here we've got a pool ball. We're going to go off the wall, creating angle 1, 2, and 3. And we wanted to determine if the measure of angle 1 equals the measure of angle 3. So let's look at this close and see that we've got an arc here. And an arc here. And what those arcs are telling us is that the measure of angle RTQ is equal to the measure of angle of PTS. So we know those are the same. How do we know? Well, that's given, right? Those arcs mean those angles are congruent. And if they're congruent, their measures are the same. So now we got to figure out how to get the measure of angle 1 and the measure of angle 3 into our equation somehow. Let's go back to our diagram. Well, we know that RTQ, let's just highlight it in a different color than green because the pool table's green. RTQ is going to be the measure of angle 1 plus the measure of angle 2. Because if we remember back, our angle addition postulate tells us that when we have a big angle that's cut anywhere inside of it, the two smaller angles will add up to the big angle. Well, so we've got angle 1 in, we need angle 3 in. Well, angle PTS is also made up of two smaller angles, so we know the measure of angle PTS is going to equal the measure of angle 2 plus the measure of angle 3. Still sticking with the angle addition postulate. Okay. Well, what else do we know from our diagram? Well, we know that the measure of angle RTQ equals the measure of PTS. We know that the measure of RTQ equals the measure of angle 1 plus the measure of angle 2. We know we can substitute the measure of angle 1 plus the measure of angle 2 for RTQ. We know RTQ is equals the measure of PTS, and we just substituted angle 1 plus angle 2 in for RTQ. Well, we also have something we can substitute in for the measure of PTS. Right here. So the measure of angle 2 plus the measure of angle 3, and that's just substitution. But we're still not there because we got to prove 1 and 3 are equal. But if we subtract the measure of 2 from both sides, we are left with the measure of angle 1 equals the measure of angle 3. So, subtraction property. So we've done what we've come to do. We're done with this problem. All right, let's move to the next one. See if we can be as lucky with this one. All right, so we have a park, a shoe store, and a pizza shop, and a movie theater. They're located in that order on a city street. So we're going to have a city street. We've got a park. We've got a shoe store. We got a pizza shop, which we can't use P or S because we already used those. So we're going to call it Z. And we got a movie theater. The distance between the park and the shoe store, is the same as the distance between the pizza shop and the movie theater. All right, so those two are the same. So let's put our little tick mark and show that they are the same. Show that the distance between the park and the pizza shop is the same distance between the shoe store and the movie theater. Okay, we can do that. So we are given that PS equals ZM, because PS is park and shoe store, and ZM is pizza shop and movie theater, and they're the same. So that's given. Let's change to blue for this next one. All right, and we got to prove PZ equals SM. This is what we're going to try to get to. So we got to bring PZ and SM into our equation somehow. Well, let's see. We got PZ right here. So PS and SZ is going to be PZ equals PS plus SZ. And that's our segment addition postulate. All right, we got that in. Let's get SM in, which is right here. So SM is going to be SZ plus ZM. So that's the segment addition postulate. Cool, we got a PZ and SM in. We got to prove them the same distance, the same length. I'm feeling pretty good about this. So let's go back up to the top where we have PS equals ZM. Because what I noticed is we have PS plus SZ, ZM plus SZ. So if I add SZ to both sides of my original given, that's just an addition property. Well, PZ right here equals PS plus SZ, so I can substitute PZ there. And let's go with a dark green. SM is SZ plus ZM. There's ZM and SZ, so SM just by substitution. We've proven what we set out to prove. We are done. All right, this one should go pretty quick. Name the property of equality that the statement illustrates. Go ahead and pause the video, solve it, and then we'll talk it through together and I'll show you the answers. Welcome back. All right. Measure 6 equals 7, then 7 equals 6, so that's just reversing it. That is our symmetric property. Let's go to the next one. JK equals KL, and KL equals 16, then JK equals 16. It's transitive property. Our favorite. So measure of 1 equals the measure of 2. The measure of 2 equals the measure of 5. So the measure of 1 equals the measure of 5. Transitive again. ZY equals ZY. It's like it's looking in a mirror at its reflection. So that's the reflexive property. So here we got AB and CD, AB and CD. We're adding FE to both sides. So this is the addition property. All right, last two. The measure of 2 equals the measure of 4. The measure of 4 equals the measure of 6. So the measure of 2 equals the measure of the 6. Once again, transitive property. All right, last one, xy equals AB, then AB equals xy. It's the same coming and going. So it is the symmetric property. Congratulations, we are done.